Hi, welcome to part 2 of module 3, and we're going to begin talking about the law of conservation of energy. So, law of conservation of energy is basically stating that energy is neither created nor destroyed, it's just changing from one form to the other. And the key is to know which form the energy that was originally in its potential is changing into as we're moving down the line. So what type? And we've already talked about the different types or the different categories that we can put energy into, whether it be thermal, electrical, nuclear, chemical, so on and so forth. And so conservation of energy was once considered the weak sister part of the laws of energy. But now, as resources become more finite and the idea of potential energy converting into unusable forms, i.e., thermal, where we cannot reconnect with it or redistribute it because it's getting into a form that it needs to be situated into other forms over long term, so it makes it hard for humans to use. It's becoming a more important topic. And so it's growing and it's very important. I can't even tell you how many companies today have somebody on staff who's in charge of just the sustainability of that company. And so the law of conservation of energy is becoming a very important form within the term of energy communities. These are the different energy definitions that all mean the same thing. So the principle of conservation of energy states that energy is not created or destroyed, although it can change from one form to another. This is another way of saying that in an isolated system of energy, you can always form up a sum, which means that if you use like the light bulb example, which I don't know if it's in this chapter or the next chapter when we talk about thermal energy, with the light bulb, the wattage that's going into the bulb is a conserved form. And then if I measure out enough radiant energy and thermal energy, I will get that same wattage. So if I have a 100-watt bulb, if I add up all the radiant energy plus all of the thermal energy, it will still equal 100 watts. So it's a conserved form, and I can always find its changing form. This says that basically everything in a system becomes interconverted. So it goes from one to the other, to the next, to the next, to the next on down the line. And it also means that as we move down the line, we tend to lose it to multiple forms. For example, when electricity is forming down the line or moving down a line, we do lose some to thermal energy and we can lose some to sound. How many times have you walked under a transformer box and heard the buzz or the sound? So we're losing it to finite resources that are not going to the end use or the exact purpose that we wanted it to go to. This is why the conservation aspect is so important, understanding that we're losing some to thermal and sound. And we want to minimize thermal and sound and keep it moving superconductor form as electrical. This goes into meeting the needs of a growing population. Obviously, this is incredibly important. As resources become more finite and the forms of energy that we have become utilized so that they're being transferred into forms that are less useful to humans, we get into this whole point of population is increasing and the need is growing. So once again, law of conservation of energy, we can assume that in an isolated system, the input will equal the output, meaning that there will be a net total energy of zero. What I put in will be what I get out. This is the light bulb example I was talking about, but we know when we utilize electricity, like in the light bulb, we might put 100 joules in and we might be getting 70 joules of light out. The rest is going to something else like heat. This also goes into the pendulum experiment. So for those of you who have taken Physics 1, you remember the pendulum experiment. For those of you who have not, I'm going to give you a quick refresher. Please look into it more on your own time since this is not a Physics 1 course, right? So the pendulum experiment basically sets, since energy is neither created nor destroyed, the amount that I put into the system will be the amount I get total. And so therefore, the length with which I pull the cord back, holding the pendulum to point A, can only be replicated to the same amount of energy at point C. And then when it swings back, it will not exceed point A. It can be somewhere between A and B if I lose a lot of energy to frictional force, but I will not exceed or gain extra energy without the addition to my system, without adding something to it, i.e. some extra energy, whether that be extra mechanical energy in the form of like a breeze comes and blows the pendulum so that we gain a little bit more energy. So this resource is finite and exact. So the three ways I can change energy in my system can fall into one of these categories. The first one is work. So the amount of energy within the system can be altered. Additions of heat, so I can add thermal to the system, or I can alter its mass, right? And we can think of this in so many ways. So work, if I have a fire burning, I can fan the fire, right? So I'm gaining the amount of work. If I have the fire burning, changing the wood in heat, I can light it in multiple places, adding the addition of thermal energy in multiple locations, right? Or finally, alteration of mass. I can add another log to the fire and make it burn slower, or I can take a log away and make it burn quicker. So that's changing the mass. This goes into energy in is equal to energy stored and energy being lost. And this lovely image right here is considered a smart home. So it is a home that is built thinking of using the sun as an energy source. And the way that they're doing that is by making sure that the sun gets the most direct sunlight during the most important time of the year, i.e. winter. So during the winter months, the sun can enter into the home, and the light can hit the home, and then within the windows of the home where it enters into the home, it can then touch things that have thermal mass. So flooring and material that absorb sunlight, things that take on thermal mass quickly or shares thermal mass quickly. Stone is a great example of this. When we touch a stone, it feels cold to our fingers, not because the stone is cold. The stone is room temperature or outdoor temperature, whatever temperature it happens to be. The reason why it feels cold is because it's actually sharing its thermal energy capacity or stealing heat from our bodies when we touch that stone. So this goes into that whole what is a good conductor, what is a good insulator, which will be in the next module. So this is in the coming chapters. Now, this smart home would also be angled in such a way that the roof line during the summer months will block out the sun. So when the sun is way up here in the sky where my little cursor is making a little circle, the sunlight will be hitting the edge of the roof, blocking out sunlight from entering the home, keeping the home naturally cool, making it so that I don't have to use as much energy to thermally control my home and instead use sunlight to do so. Given an example of this smart building is this functional structure that they have down at the McCoskey Center in Slippery Rock University, which is part of the Penn State University holdings. So this is part of Pennsylvania State Universities, and this is one of the places that I worked on my master's degree and one of the places that I lived and learned a lot about sustainable structures. This is a living experiment. So what this is a building that was retrofitted to meet sustainability needs so that we can live off the grid. And everything in this home is tallied. And so I'm going to give you a quick walkthrough of this experiment, and a lot of papers and research is being done, and the guinea pigs in this experiment are the humans that are living there trying to survive within this functional structure. And so right away you can see it's built so that sunlight is maximized during the winter months because of the angling, and the roof is in the way, and so it's minimized during the summer months, keeping the building cool in a natural form. This here is actually normally a wind turbine, this lovely structure here, and you'll see that way later on in the chapters. I'll show you the wind turbine that we built that goes on top of this housing that's right here that I have. You can see the mini solar panel here. That's just running something small within the building. There's a bigger housing of solar panels that I'll show you. And now here are all the gardens, because this is a full experiment. So the sustainability went beyond electrical energy, which is what I was doing, and into non-conventional and conventional forms of just food consumption and that sort of sustainability. So on that note, I will pick you up walking you through this functional experiment on sustainability and the laws of conservation and energy in a part 3.